Linear regression or prediction. The basic idea of regression analysis is to use data on an independent variable, also known as predictor, to predict or explain variation in a dependent variable. We've already seen that we place the dependent variable on y-axis represented by y, and x-axis we have the independent variable represented by x. We draw a line, a straight line, and that determines the relationship between y and x. And then we determine two more things. One is the intercept represented by beta naught. So that is the point where x is 0. So the value of y when x is 0. And we calculate another thing, what we call it as slope. So that is the change on y divided by change in x. So that is the steepness of this line represented by beta 1. This beta 1 or slope also tells us the change in y while x changes to 1 unit. Linear model, yij is equal to beta naught plus beta 1 xi plus eij, degrees of freedom, that's equal to 1 plus 1, and for error term it's ij minus 2, where yij is the jth observation receiving ith treatment, beta naught is in the intercept, value of y when x is equal to 0, beta 1 is slope, a change in y when x is increased by 1 unit, and eij is the error term, error associated with the jth observation receiving ith treatment, and NID 0 sigma square. Prediction function can be written as y over head sign. So we can predict y like this. There is a component beta naught intercept, and this head sign means the estimate for that, plus beta 1 head sign into x, where beta naught head and beta 1 head are estimates of beta naught and beta 1, intercept and slope. The estimate for beta 1 we can calculate as the sum of the cross product of the deviations of x from their means and y from their mean, and we do it in pairs. We take each number from x and y, and for that pair of number we calculate their deviations from their respective means and multiply them, and in the end we sum for this whole thing. So that is also known as the cross product, sum over x into y, this cross product, and divided it by this xi minus x bar square, sum of it. So that is the sum of the square deviations for x, represented as s into x and x, and we can calculate this this intercept as beta naught hat. So that is equal to y bar minus beta 1 hat into x bar. In simple linear regression, we have one slope beta 1. There is one intercept in both of them. So beta naught plus b1 xi plus ei. In this estimate shape, there are the proper the model shape using the Greek letters. It's beta naught hat plus beta 1 hat xi plus e hat sign I. The common way of writing this is yi is equal to b naught plus b1 xi plus ei. So that is the shape that we use. This is while we are writing the model, are we talking about the populations. And the equation for prediction also modifies like y at sin I, that's equal to beta naught plus b1 xi. In multiple linear regression, as we said, the intercept is 1, but there are more slopes. So beta 1 x1, beta 2 x2, and up till uh, the other. Uh, so there are more predictors in fact. So for each predictor we have its own slope. Let's understand the linear regression with the example 11.2 from the book. So data from a sample of 10 pharmacies are used to examine the relationship between prescription sales volume and the percentage of prescription ingredients purchased directly from suppliers. So we have sales represented by Y, purchases represented as X. So we are looking for the effect of purchases on sales. So the relationship between the sales volume and the percentage of prescription ingredients. So Y depends on X. So here we have the sum of the Y's. So all those Y's. So we have 10 numbers over here, and both sides we have equal numbers. And in fact we have 10 pairs of numbers. So Y on this side 25, X here is 10. We can calculate the deviation of Y from its mean, Y minus Y bar, deviation of X from its mean, X minus X bar, and we know that the sum of the deviations is equal to 0. Same way we can calculate their cross product. So deviation of Y from this Y bar, this number, and X from its X bar, and we multiply them, and the thing which we get it is called cross product. So this is the cross product for these two numbers and for these two, and we take all those cross products for these 10 pair of numbers, and then we sum them up, this total cross product, sum over X and Y, and then we take these deviations for X from its mean and we square it. So square deviations for X, and then in the end we sum them up. So then finally we get the sum of the square deviations for X. Plug in these numbers into these equations, and the slope we get is 1.97, and the intercept is y bar minus beta 1 hat into x bar. So y bar, the mean for y was 71.3 minus 1.97 into the mean for x 33.8, and the slope we get is 4.70. We put it into the equation. So that's y bar, this y hat is equal to 4.70 plus 1.97 into xi. So that is the equation for prediction, and we can calculate the y at any value of x. So for example, we plug in the value of x as 15%, and our y for this number 15 is 34.25. So that is $34.250. So while plugging any number for x, we can predict y predictor, and this is the thing that is predicted. That's why this regression is also called as prediction. There is another very important parameter that's called as coefficient of determination, r square, capital R square. That's we can take this small r and square it, and technically it's the variance predicted by y value divided by variance predicted by x value, or we can also define it as the proportion of variability in y that is described by a linear relationship between x and y. That is the model. So linear relationship between x and y, the model, it is a measure of the goodness of a model. How good is this model in explaining the variability in our data set? It ranges between 0 to 1, 1 being excellent. So close to 1, that means our model is good. So any number close to 1 means we applied a correct model. So for example, you apply ANOVA, or you apply t-test or any other thing like correlation, regressions, and finally you calculate. How does this correlation and prediction works in gene networks? So for example, we have two genes and we draw their expression profiles and we see that these two genes, they are expressed similarly. The y-axis we set it in log scale because gene expression has a big magnitude of differences. But if you see those uh, these genes, the expression pattern seems similar. Our correlation between them is 0.998, a strong positive correlation. So they are kind of what we can say is they are co-expressed, gene 1, G1 and gene 3, co-expression. We can plot them like this, one on x-axis, one on y-axis, and we observe the straight line. So R is 0.998, that is the correlation, and this is the equation for prediction, 4.9738x, that is this one is the beta 1, the intercept, and this is the slope, and R square is 0.9978, so that means the model is really good, and we fitted a good model. It's 99% explaining the variability in the model, and there is a strong positive correlation. If you look into these two genes, the expressions are kind of flip around. The correlation is minus 0.998, so negative, a strong negative correlation between G4 and G5. One is going down, the other is coming up. So the expression pattern seems like um, kind of negatively regulating each other, and we can say there is a co-expression and a correlation. And when we draw this straight line, one of the gene is on x-axis and one on y-axis, so we draw a straight line going down, so that means a negative relationship, and this is the value for their slope. This the slope is negative plus the intercept is this number 13.467. So the point where this this x is 0, so the value of y when x is 0, and the r square coefficient of determination, that's 0.9976. Again, the so we can use these correlations in the gene networks. Here we have the 5 genes, G1, G2, gene 3, gene 4 and gene 5, and we construct a matrix like this, same genes on the rows and on the columns, and the data points in between, these are the correlations. So this is for example between G1 and G2, G1 and G3, G1 with 4 and 5, here is G2 with 3, 4 and 5, G3 with 4 and 5, and G4 and 5. So these total relationships which are important for us, the between the same gene doesn't make any sense, so we don't need this diagonal thing. The only numbers which we need is half of this matrix, the total matrix. If we take it, that's the duplicates of the same relationships. So total we get over here is those correlation values are the pairs which we can construct over here, since we do these pairwise comparisons, and we get those correlation values. So G1 goes with these rest of the 4, and that is 4 of them are here, 3 are here, 2 and 1. So total numbers we have over here is 10. So if we have 5 genes, it's 5 into 5 minus 1 by 2. So that is equal to 10 pairs of those relationships are here. We can represent this thing in this diagram called as heat map, and again this heat map is where we can either go for the top half of the region, or we can go with the lower one, but everything is shown here. So all those relationships, and obviously in between This heat map, you see more heat because this is the same gene against itself, again same genes against itself. Now, the negative correlations are shown in blue, whereas the positive correlations are shown in red. So we can construct a heat map like this to infer the relation, and then we can pick up the spots where the more heat is coming. So for example, G1 and G2, you can see it here in this region, and G3 and G1 in this region. So obviously G1 and G1, that it doesn't make any sense, so we ignore this thing, and but we can take this region, that's informative. Alright, and we have other genes here, G1 with G6, C7. So these are the regions, or these are the genes where we see those negative correlations between them. So that is the information which we can infer from this heat map. We can construct the gene networks also. For that, we need to transform this matrix into this form. So we have gene A, gene B, and then correlation. So A means the first gene, and B means the second gene, or we can also call them as source and target and correlation, source, target, correlation, ST and core. So G1 with G2 correlation is 0.573, G1 with G3, G4 and G5. Now we can take all those genes and put them as those circles or dots in a shape of a network. So since G1 is connected with all of them, so we what we do is we place it in the middle, and we represent all those genes with the dots, and we draw those lines between them. So these lines, they determine their relationships between each other. A positive correlation, we represented here with this green line. These lines are called as the edges in network language, and these dots are called as the these data points, are these genes are the nodes. So in the network language, we call them as nodes. So we have 5 nodes here, and we have 5 edges here. So the thick edges represent a strong relationship. Color indicates positive or negative. So thick green, for example, is a strong positive relationship. So that's here and here. It's a relatively thin edge. So sometimes we take these edges and their thickness, and we modify that as show it as a proportion of, or a strength of this correlation as well. So the red colors indicate a negative correlation. So G4 and G5, a negative correlation, and G1 and G4 as shown in this data set. Between G5 and G4, we have not seen it here in this matrix, but it is there. I'm only showing the top part of this matrix. So between G1 and G4, again there is a this thick red color edge, so strong negative correlation. So this way we can draw those gene networks. So far this course was covering all of the basic stuffs. The statistics is divided into descriptive and inferential. In descriptive, let me recall, we described the data. So we talked about center tendency, mean, mode and median, and whichever is the best estimate in whichever situation, we discuss that. Variability, we can measure with the variance in standard deviation and range, we covered that. And then relative standing, where everybody stands in a distribution. The relative positioning, we got it by z-scores and percentile ranks. And the inferential statistics is where we do the inferences about the population. We're using the data from the samples. If the IV means independent variable, DV means dependent variable. If both are continuous, we can do, if we're following the parametric approach, we can do those Pearson correlation where we are using the means in our equations. So we covered Pearson correlation and regression, and in non-parametric, we might use medians, Spearman and Kindall. We did not cover that, but that's what we do. If the independent variable is categorical, independent variable is continuous, parametric case, we do t-test and ANOVA, we covered that. And there is ANCOVA also, analysis of covariance, we did not cover. And in non-parametric, there is sign test, we have seen that. And then there is Kruskal-Wallis test if you have more distributions. Um, this we did not cover in this course. It's a relatively advanced topic. Continuous, both are independent variable is continuous, independent variable is categorical. In parametric case, it's the discriminant analysis, and non-parametric is point by serial correlation. And if both are categorical, we do chi-squares, we covered that. And there is also a phi coefficient, we did not cover. Slide credit for this slide was I give it to my student Noman. He is enrolled in first semester of bioinformatics. Thank you so much. Overall, we covered a lot of things over here, and that's pretty much for the basics of this statistics.